Hello, everybody. I'm doing this recording for the last part of lecture two, because I understand that the classroom recording did not capture the last part of the lecture. I understand that it has stopped at slide 88. So instead of starting from slide 88, I'm just going to cover the last topic on lecture two, which is on Greeks, right? Okay. So in case for those who have already or was at the physical lecture, and you find that there's no need to re-watch this recording, that's fine, because there's the topics that or the conversations that we have will be the same as well as what we have covered in the physical lecture. All right, it's mainly for benefit of those that want to, first of all, re-watch it, or could not make it for lecture two physically. Okay, so let's look at Greeks, right? So lecture two, we have covered quite a bit on the various um, factors that could affect the price of an option. So the last part that we're going to talk about is Greeks. So mainly we're going to talk about a few things, delta, theta, rho, vega, and gamma, right? As you can see here, we'll go into detail what they mean individually, but as a broad overview, delta basically means this change in the underlying, which will affect the option price. Uh, Theta is the change in the time to maturity. Rho is how the interest rate changes, which will affect the option price. Vega is volatility, how market volatility could affect the prices as well of the option. And last but not least, gamma, which is the second order derivative of delta, right? Sorry, have not yet turned on my camera. Okay. Okay, let's go to delta. So delta is the change in option price with the change in the price of the underlying, right? And of course, we know that underlying is a stock. So generally, the idea behind what's being discussed here is that if a dealer is going to take a short position, right, on a, let's say, a call option, you want to actually cover your call option. And one way to cover a call option is to do a delta hedge, meaning that you buy X number of shares, equating to the short position that you have taken, right? And this is delta number of shares, X number of shares given by this thing called delta, right? So the higher the delta generally means that higher exposure of your options, in this case, the short call option to the market. Generally, delta ranges between 0 and 1. Just to take note, for a put, it becomes 0 to -1, as we'll see in the next slide. Okay. So as you can see here, the delta that is out of the money goes to 0. For call, it goes to a maximum of 1. But for put, it goes to a minimum of 0. Delta hedging. So even if, so what are we trying to say here, right? So even if we have a delta neutral portfolio, meaning that if you take a short position, we buy X number of shares to cover our delta position so that it's delta neutral, we do have to consider various other components of the Greeks, right? So earlier we saw there is gamma, which is the second order, delta, which we'll talk a little more in the later slide. And we also need to consider things like the volatility, right? Vega, and also the time decay, right? How the shorter time to maturity will actually affect the price of your options as well. So there are various considerations that we will have to take into account in order to ensure a perfect hedge. And so if we do not consider Vega, which is actually very tough to hedge, then it might be actually very hard to be a perfect hedge for our short position. Okay. So a good representation of how delta looks like is basically giving you the gradient on the price as the option. Recall in an earlier um, part of the lecture, we talked about how the price of the option is a curve like this, which was a combination of the intrinsic price plus the time value of the options. So in the same sense, the price of a call option is a curve, and or not really n, but the delta is basically simply just the slope, which is given here. It's a slope. And because it's a slope, do you notice that this slope, right, which is equal to delta, would always underestimate the increase in price? Can you see? Underestimate here. This is the delta, but then actual is here. And underestimate the or overestimate the decrease in price. Sorry, overestimate the decrease in price. Can you see a decrease this here, but actually the original is just here, right? So I repeat again, the delta generally underestimate the increase in price and overestimate the decrease in price. This is important. I forgot to erase this, and this is what I try to say here. So there's an error in the delta which is symmetrical in both direction, right? It underestimates the increase and overestimates the decrease. And so this error is basically what we call the convexity, which is the second order delta, which is how curved the price of option is, right? Because our price of option is given by a curve, right? So there's going to be some curvature of our profile such that it is just estimating the delta, which is a straight line, is going to give us some error. So there's some relationship between the delta and time to expiry as well, which is quite interesting, right? So as we see here in the graph, we see that the delta is going to be the steepest. Okay, so let me show you. So there are three things: 10 days, 30 days, and 60 days, right? The delta is very steep at the 10 days compared to the 60 days, right? The different color in the line. So what's it trying to say here? And of course, this is very close when very close to exercise price. If it's further away, but to exercise price, the 10 days continue to be steeper than the sorry, the 10 days sorry, this let me repeat again. The even before exercise price, the 10 days continue to be steeper than the um 60 days. But of course, this is you can't really see it so obvious as compared to see it closer to the exercise price. So what does this mean? It means that there's going to be a sharp change in the delta, and the position will be very hard to hedge when our option is short-lived and at the money option. So it's very close to exercise price here, and it's just going to expire soon. So it's going to expire soon, and it's going to be in the money. That will have the highest delta. So gamma is in a proper way to put it, is called a deviation in exact price, exact option price, change from the price of the option as approximated by the delta, or in simply says that's the second derivative of the delta. So it shows the convexity of how the option price changes. And the interesting thing about convexity is that it's always positive, right? Because it's how convex your option or your option price is on the graph. So the delta of the option become more positive towards one when the stock price rises and more negative when it falls. This is what we have seen in the graph earlier. So important thing is that, again, I repeat, for a gamma, it's always positive and ranges from 0 to 1. So in a situation where the delta position were risk-free, meaning that the delta is perfectly hedged, then there'll be no gamma, right? However, we know that in most real life case, there's always going to be a gamma because our delta position is usually not perfectly hedged. So similar to your delta, where it is usually the highest close to expiry and near the money or at the money. For your gamma, it also occurs when the highest gamma change is going to be happening when it's occurring near the expiry, right? And when the delta is at the money, is when it's at money option. So it's very similar to your delta. So as we can see in this graph, what's important is that we see there's this $25 call for gamma, right? So we know that this is 25, which is the exercise price. So as we go closer and closer to the exercise price, so the stock price keep going closer and closer, you see the gamma increasing until the highest at the point at the money, right? Meaning at 25. So that's the highest level of gamma that we have, which is the point where we have also the sharpest change in your delta. And so because the gamma is the highest, this rapid movement will generally cause your delta hedger to have issues trying to achieve a perfect hedge for your delta. However, if we are at extreme ends of the range, meaning out of the money or very in the money, then our delta and gamma are generally in the extreme ends as well, meaning that there's not going to be a large movement of our gamma. So in this graph, we see that time to expiry, right? So December, October, September. So September, very close to expiry. Imagine now we are in July, right? So July to September is the shortest. And so that's why we have the steepest profile of our gamma. And of course, it is the highest at the strike price of 45 if it is a 45 dollar call. And then for your October and December, you see that it's a bit more gentler because the time to expiry is further. So highest gamma happen when short-lived and at a month. So it's very similar to our delta. All right. For Vega, so Vega is the sensitivity of the option to volatility, right? And generally, we know that volatility is very positive for option simply because options are one-sided bet. So higher sensitivity gives us possibility of the option being in the money. However, if it's out of the money, we typically do not lose money if our bets are in the right direction. Okay. What's interesting for Vega is that generally in the Black-Scholes model that we covered, this is kind of a static number. However, we know that volatility in the market changes dramatically day by day, and so it actually makes the model, such as Black-Scholes model, really hard to estimate the price of option accurately because our volatility changes. So a comment here, change in volatility greatly changes the dealer's position. So delta hedge position with zero or insignificant gamma can greatly change with change in the volatility. Like I mentioned in the physical lecture as well, generally these formulas they're not too important, just for you to know what they are, right? You are not really required to know how to use a formula in questions. As you can see here, for both the call and put, volatility is positive for the price of the options. So comment here that for Vega, the price of option is more sensitive to volatility when it is at the money, right? So we expect, of course, if it's at money, then any change in volatility could put it in the money, and therefore immediately we can exercise the option. So there's some positive benefit to volatility, and this positive benefit is the greatest when we are close to the exercise price. Final comment is that if a dealer wants to ensure a perfect hedge, they must ensure that it hedges their delta, gamma, vega continuously to achieve a perfect hedge. If not, we will not be able to hedge it. For roll is basically the time to maturity. And as we talked about during the earlier lecture, we know that time to maturity will affect the PV as well as it has some benefits in terms of optionality, right? So which is why we see the time to expiry. Oh, sorry. My bad. Sorry. Roll is not that's theta is the time to expiry. Roll is on the risk-free rate, right? So the risk-free rate is we kind of talked about it in the earlier lecture as well because we are going to discount our strike price, right? So for the call, the increase in risk-free rate will benefit its price because it's ST minus X, right? So as our risk-free rate increases, our X, discounted value of X, decreases, which increase the value of our call. Now our put is X minus ST. So as our X, the discounted value of X decreases, our value of the put decreases naturally as well. Theta, which is what I talked about earlier. Apologies on the mix up, but for theta is basically a time to expiry, and generally we know that as the time to expiry decreases, the chances of the option being in the money decreases as well, which decrease the value of the option. However, I just want to caveat this to say that we need to consider first optionality, which is what we earlier mentioned, as well as the PV effect as well. Okay, so that's all I want to cover. Again, thanks for watching this recording. This is particularly to help those that were unable to make it during the physical lecture and hope to watch the recording for what the classroom recording did not capture. All right, so thank you and all the best for your class tests.